Imagine a world where quantum computing harnesses the power of light to revolutionize how we solve complex problems. Integrated photonics for quantum computing is on the brink of making this vision a reality, offering a compelling alternative to superconducting quantum computers. But here's where it gets controversial. Some experts argue that photonic systems might just outperform their superconducting counterparts in specific applications. By Abdul Ahad Nazakat, reviewed by Louis Castel, August 8, 2025. While superconducting quantum computers have dominated recent advancements, integrated photonics presents a unique approach that leverages photons instead of electrons. This technology operates at room temperature, unlike superconducting systems that require near absolute zero conditions. Photonic qubits also maintain their quantum properties longer and are more resilient to environmental disturbances. The beauty of integrated photonics lies in its ability to apply established semiconductor manufacturing techniques to build quantum circuits on silicon chips. This addresses critical challenges in scaling up to millions of qubits, integrating multiple components onto a single device, ensuring reliable operation, and creating commercially viable systems. It's particularly suited for applications where operational consistency is more important than raw computational speed. CMOS manufacturing and miniaturization advantages. One of the most significant advantages of integrated photonics is its seamless integration with existing semiconductor factories. CMOS fabrication techniques allow quantum devices to be built alongside classical electronics, using the same infrastructure that produces computer processors and smartphone chips. Unlike other quantum approaches that require entirely new manufacturing processes, photonic systems can leverage existing facilities, reducing production costs and development time. Integrated photonic circuits miniaturize quantum systems to chip scale, making them more stable and manageable compared to bulky room-sized optical setups. By placing photon sources, processors, and detectors on a single chip, manufacturers can eliminate lossy connections between components, improving reliability and reducing system complexity. Traditional bulk optics systems require constant realignment and are highly sensitive to vibrations, whereas integrated systems are built to withstand environmental disturbances through solid-state construction. Advanced materials enable low-loss performance. The success of integrated photonics hinges on materials that minimize light absorption. Silicon nitride and lithium niobate have emerged as leading choices for quantum waveguides, maintaining quantum information integrity over longer distances. Recent advancements have achieved coupling efficiencies above 90%, significantly boosting overall system performance. This means more quantum information survives processing, leading to more reliable computations. Performance comparison: photons versus electrons. Photonic systems have distinct characteristics that set them apart from other quantum technologies. Superconducting qubits operate faster with nanosecond gate times, while photonic systems boast longer coherence times and easier qubit connectivity. Trapped ion systems connect all qubits directly but run slowly. Photonic qubits scale with standard manufacturing but require indirect methods for 2-qubit gates. Mid-circuit measurements are straightforward in superconducting systems, but pose challenges in photonic designs due to the difficulty of storing photons. These differences make photonic systems ideal for specific applications rather than general-purpose quantum computing. Essential components for photonic quantum systems: high-brightness single-photon sources. Quantum dots are a prominent technology for generating photons on demand, with devices capable of producing over 10,006 pairs per second per milliwatt. Parametric down conversion is another method that generates identical photons required for quantum interference. Ultra-sensitive photon detectors. Key detection technologies include superconducting nanowire single-photon detectors, SNSPDs, which achieve detection efficiencies over 98%, and single-photon avalanche diodes, SPADs, a compact alternative suitable for on-chip integration. Quantum logic gates and circuits, interferometric circuits, composed of components like beam splitters and phase shifters, form the basis of photonic processors. These circuits manipulate quantum states to create the interference effects necessary for computation. Current performance benchmarks. Leading photonic systems have reached key performance thresholds essential for fault-tolerant operations. Single photon source brightness, 10 to the 6th pairs per milliwatt. Detector efficiency, 98%. Coupling efficiency, 90%. Photon indistinguishability, 99%. Logical error rates, 10 to the -3. Challenges in scaling photonic. Lack of native photon interactions. Photons do not naturally interact with each other, complicating the implementation of 2-qubit logic gates. Specialized architectures, such as those based on measurement and ancillary photons, are needed to mediate these interactions. Multiplexing overhead. Scaling to a large number of qubits requires the complex multiplexing of many single photon sources, adding significant overhead to the system's control and timing architecture. Current approaches include time bin and frequency domain multiplexing. Hybrid integration. Integrating different material platforms, such as quantum dot emitters with low-loss silicon nitride waveguides, remains a significant fabrication challenge. Overcoming this is crucial for producing scalable sources of high-quality photons on chip. Real-world applications. Photonic quantum computers excel at simulating molecular systems, providing insights into complex molecular structures and reactions that are beyond the reach of classical computers. Applications include designing new pharmaceuticals and developing advanced materials with specific properties. In finance, photonic quantum processing can optimize complex tasks such as portfolio optimization, risk analysis, and trading strategy development. The ability to process large datasets rapidly gives financial institutions a competitive edge in decision-making. In supply chain and logistics, photonic systems can optimize routes, manage inventory, and coordinate supply chains more efficiently than classical computers, reducing operational costs and improving efficiency. Photonic systems are also ideal for secure communications, as quantum states of light enable unbreakable encryption for sensitive data transmission. This capability is invaluable for government communications, financial transactions, and corporate data protection. Integrated photonic platforms support chip-to-chip quantum networking, enhancing the robustness of quantum networks and enabling hybrid quantum systems. What's in store for integrated photonics? Currently, photonic gates operate probabilistically, limiting system efficiency. Developing deterministic photon-photon gates could remove this constraint and significantly enhance performance. Photonic fusion-based architectures offer the potential to reduce resource overhead for fault-tolerant operations, making large-scale photonic quantum computers more practical. Integration with AI inference chips could lead to advanced photonic neural networks, combining quantum processing with artificial intelligence to deliver superior computational capabilities. On-chip quantum sensing platforms could improve precision measurement, opening up applications in medical diagnostics, environmental monitoring, and navigation systems. Future outlook. The commercial potential of photonic quantum computing is currently driven by applications in secure communications and molecular simulation. Further progress toward fault-tolerant systems depends on overcoming technical challenges in material performance, component integration, and error correction. Research efforts are focused on specific solutions, such as developing deterministic photon-photon gates to increase operational efficiency and fusion-based computing to reduce resource overhead. Other potential applications include on-chip quantum sensors and hybrid systems integrated with classical AI hardware. The primary advantage of integrated photonics as a scalable platform is its compatibility with existing semiconductor manufacturing and its ability to operate at room temperature. The company's future market position will likely depend on its ability to address fabrication, integration, and fault tolerance challenges. What do you think? Will photonic quantum computing become the dominant force in the quantum technology landscape? Or will it remain a niche player? Share your thoughts in the comments below.